water.
The reason I want to start right on time today is because at 10 o'clock we have to be out of here. We have a meeting that is coming in right at 10, and they requested that we vacate the room at 10 o'clock so they can set up the room. So with that, it is a pleasure to have our two speakers over from Wenck today, who are going to be talking about stormwater and how to treat it for microbiological removal. And you know, this is something that I think we're going to be seeing a whole lot more of, is in the fact that stormwater is becoming this increasingly important parameter of, you know, conveyance of contaminants to our surface water. And so I think there's going to be a whole lot of interest in your talk. So we have Ed Mattheisen here, who has worked with Wenck, he tells me, for 16 years, quite a while, and Lou John, who is going to be doing the lion's share of the presentation, I guess. So with that, Lou.
Thanks, Mark. Morning, guys. Today our topic will be.
You're going to go over that?
No, you're fine. Oh, I should be. Where should I stand?
If you can stand over on that side, then it picks it up on our camera.
Yeah, this black one.
Yeah.
I was going to say that's facing like my back. Yeah, it kind of is, but wondering. Today I'll be talking about the use of biochar and iron-enhanced sand to remove bacteria and phosphorus in the urbanized watershed. And this is a project for Shingle Creek and West Mississippi watersheds. And it's worth mentioning that it's funded by the EPA 319 grant. And throughout the time period, we received a lot of technical assistance from Dr. Andy Erickson, John Gulliver, and Beth Fisher from University of Minnesota, as well as Dr. Sanjay Mohanty from UCLA. E. coli, so for Shingle Creek, first of all, it's a highly urbanized area, 67 miles, square miles for both Shingle Creek and West Mississippi watersheds. It's located in the Twin Cities metro area. And looking at the water resource, the surface water, there's a lot of impairment that exists in the two watersheds. Out of all the surface water resources, 10 lakes are impaired for nutrients. Shingle Creek, Bass Creek, which is the bold red line in the center, is impaired for bacteria chloride, dissolved oxygen biota, and Mississippi River, which is the ultimate discharge point for the two watersheds, impaired for bacteria and turbidity. So being a large watershed, highly urbanized, we have a lot of non-point source discharge for stormwater. 50% of the watershed, the stormwater coming out of the watershed is untreated. This makes it very difficult to target a location where a concentrated discharge will come out and for treatment. So our goal here is to develop a method that's able to remove bacteria and phosphorus from stormwater runoff passively and economically, and of course we're interested in knowing its effectiveness. So to take a step back, we want to look at why it's important to remove bacteria and phosphorus, why that's an issue, and looking at how we're going to remove it. So first of all, bacteria, they are one of the first organisms that exist on Earth. They naturally exist in lakes, streams, and other different environments. Some bacteria cause health concern, such as E. coli. I'm sure you all heard that E. coli outbreak in romaine lettuce that is on the news everywhere. And that's why we applied for apply a standard for our water resources to make sure that E. coli level is not raising a health concern. And that standard chronically is 126 CFU per 100 mil, and there is also a acute standard that's 10 times higher than that, 1260 CFU per 100 mil. And unfortunately, Shingle Creek and parts of Mississippi River have E. coli that is exceeding the standard, deeming it impaired. So E. coli comes from all sorts of sources in the urban environment. These are two of my dogs, and they, of course, contribute E. coli when they. So they come from pet waste, wildlife waste, failing septic systems, sanitary leakage, and overflows. And this is the current condition for Shingle. It's not as current, but this is a box plot for available E. coli samples from 2007 to 2012. And the location of this water quality station is right, there's a little map on the side, it's right at the mouth of Shingle Creek. So looking at the box plot, the mean, the little blue line is 150 CFU per 100 mil, while exceeding the chronic standard. And the whole data set ranged from 10 to 27,000 CFU per 100 mil. So we have a lot of E. coli discharging in the Shingle Creek. This is from the TMDL, the load reduction curve. So you can see that low standard is a red line, where a lot of the samples from mid-range to mid-range to high flow that is exceeding where the load supposed to be. Now let's look at phosphorus. So again, phosphorus naturally exists in lakes and stream systems. However, it's a very important nutrient. I'm sure you all know that the freshwater systems that it can cause eutrophication and algae bloom. And there's a picture of algae bloom at Upperton Lake, which is a shallow lake in Shingle Creek. It's 2017. And phosphorus also comes from different sources, such as plant and leaf litter, soil particles that legacy phosphorus can be attached to, pet waste, fertilizer application on your lawns. And the TMDL is requesting that between 10 to 83% of TP total phosphorus load needs to be reduced to achieve the standards. And Shingle Creek is not yet listed for phosphorus, but it's kind of right at the standard. So because this watershed is highly impervious, there's very limited opportunity for us to apply apply any of the new opportunities for structural BMPs, and we have a pretty aggressive goal for reduction of nutrients, sediment, and bacteria. And now we need to think out of the box that how can we utilize existing structure, or how can we modify any structure to be able to achieve the goal. So start with sand filters. We used to use in ancient times, or even now, we used to use sand filters to filter water for drinking purposes. And what if we modify that media with some other material to be able to achieve additional reduction goals for pollutant? And when I mentioned biochar, first of all, I want to sidetrack a little bit and talk about a research that kind of is the start of this study. So this is one of the first research that people did to look at the effect of biochar in removing E. coli. So first of all, what is biochar? Biochar, it comes from plant material, any woody material, or even straw leaves that can do too. You heat it up in an oxygen-free environment. So the difference between biochar or charcoal is you burn the wood with oxygen, and biochar is you burn it without oxygen. It's usually this little metal tank that you heat it up. And that process is called pyrolysis. When you're heating it up around 500, 600 degrees Celsius, it's called slow pyrolysis. It creates a smaller size, but it's not too small, of biochar. But if you heat up any further, such as 100 or 1,000 degrees Celsius, it would reduce the grain size to a really fine powderish. So the nice thing about creating biochar is that so this process is called pyrolysis. I'm going to refer to it as pyrolysis from now. Pyrolysis process actually make the primary porosity of the biochar even larger. So primary porosity is the surface area within a single grain. So it creates a large surface area that's able to get more molecules or pollutants attached to it, therefore removing it in a physical way. So the start of biochar is originally used as a soil amendment. So in agricultural world, there's a lot of use of that to retain moisture in the soil, to retain nitrogen. It will be able to hold on to nitrogen a lot longer before it leaches down to the groundwater. And kind of to summarize what biochar can do, in addition to promote this attachment of contaminant with the surface area, it also is a great source for carbon sequestration. It's a slow release of carbon back into the atmosphere to retain more carbon within the soil itself. And it also captures nutrients and slow release it to increase soil fertility. So Dr. Sanjay Mohanty from UCLA started the research by trying to answer a few questions about biochar. So does biochar remove E. coli? What's the effect of intermittent flow in mobilizing E. coli attached to biochar? What about natural organic matter that exists in stormwater? And does biochar provide ideal environment to support the growth of E. coli? And in order to answer those questions, they have this lab study that's set up with the column studies. So they have the column on the far left side is sand, and then the two middle ones biochar, and the right side is the iron filings. And then they run synthetic stormwater with E. coli in there from the top, and then collect the outflow from the bottom for sampling analyses. And what they found is that biochar is actually capable of removing 99% of the E. coli from stormwater, and with just sand, it was only able to remove 60% of the E. coli from stormwater. And natural organic matter decreased removal, increased mobilization, but less severely compared to other geomedia, such as iron oxide coated sand. And the intermittent flow is able to mobilize a small fraction of E. coli. And however, E. coli could potentially raise the pH of stormwater. And there's the reference if you're interested in looking at that study. So iron hand sand to remove phosphorus is pretty commonly used in Minnesota. And this iron hand sand filter, also known as Minnesota filter, is to allow filtration to remove additional TSS and phosphorus through the iron hand sand media that is in that little box over at the normal water level surface over on the left side, and allow drain tiles to carry the treated water out. So when the water it's normally built around the normal water level, so the water level in the stormwater pond rises above that, it will allow filtration through the filter bench itself. So the chemistry of the iron filings removing phosphorus, it formed a strong chemical bond that is very hard to break, and it settles. However, ferric hydroxide is also a very strong bond that can form at the surface that might prevent water from flowing through the media itself. So there's a lot of frequent maintenance involved in this kind of filter structure. So these are all proven effective in the lab, and what we really want as consultants to see in the field, how does that work? Because in the lab you have way more controlled environment than in the field. Therefore, our implementation study comes to, so the two types of media, we listed all the sources. So the iron hand sand is 5% by weight from the literature values, and is purchased from placed companies, and is pre-mixed. Biochar is purchased from Char Energies, northern Minnesota, and is made from a mixed hardwood at 500 degrees. So it's low pyrolysis, you can see that grain size. If it's 1,000, it will be all those tiny, fine material. And based on the literature value from the research from Dr. Sanjay Mohanty, we use 30% of biochar by volume. So 30% biochar, and the other 60% is iron hand sand. And we have a few different field demonstrations. Just want to capture stormwater at different levels before it discharges back into the stream. So first one is the catch basin media insert. So it's placed near the catch basin to try to capture the first level of runoff coming from the street, coming from parking lots. And the second level is the pond filter bench. So when the stormwater runoff gets conveyed through the storm sewers and end up in stormwater ponds, we want to provide additional benefit to the pond to remove nutrient. And the utility box filter, you'll see the picture later on, that is actually a stream diversion box next to Shingle Creek. So that would be our last level of treatment before discharge into the Mississippi River. So here's a schematic of the skimmer box that we used at the catch basin inserts. So we drop those in the catch basin and place media inside of those. I'll have a picture later on. And so inside we kind of have a sandwich structure. We have iron hand sand on top and bottom, and then we'll have the biochar in the middle layer to prevent any floating or loss of material. However, if biochar is completely saturated, it will not float. So this is just some field pictures of what the box looks like. That's the first layer of sand, and then biochar would be placed on that, and another layer of iron hand sand will be on top of that. And this is the skimmer box at work. You can see this is during a rainstorm. You can see the storm water coming off the parking lot that is flowing into the skimmer box. And that actually requires quite a bit of maintenance as well, because there's leaf, there's trash, and I found some kind of, I don't know, leftover fast food in there too. So as to sampling, it's really tricky to sample these kind of skimmer box. So our best shot was that, you can see it on the left side, we installed a little metal tray on the bottom trying to catch water coming, seeping out of the sides, and then we attach, so we drill some holes on the bottom, attach a sampling bottle, so attach the bottle cap, and so we can screw it on and screw it off to capture stormwater runoff after treatment from that catch basin. It actually works pretty well. There is one problem with that I'll talk about once we look at this. So this is the result that we measured from 2016 to 2018. We don't have a whole lot of data points because E. coli, it only has an 8-hour holding time, and we don't necessarily get convenient rainstorms here. So usually it rains overnight and the lab's closed. So you can see that this is the total phosphorus removal. The blue is the water coming in, and the orange is water coming out. We really don't see any removal from this device, so it's not as effective. There's only one event that was able to remove some of the phosphorus. And dissolved phosphorus is kind of a similar trend. However, E. coli removal looks really promising. From 2016 to 2018, we have maybe maybe 3 events that is not removing E. coli. However, majority of it is removing E. coli on a very large scale. So just to summarize our results, our average removal efficiency to date is worth mentioning. There's 2 colors because we have 2 skimmer box implemented. One is in New Hope, one is Robbinsdale. New Hope is treating the street runoff. Robbinsdale is treating the parking lot runoff. And from these 2, E. coli removal, so on the days where it's being removed, New Hope is able to achieve an average of 64% removal. Robbinsdale is able to achieve an average of 92% removal. And for total phosphorus, the 42% is that one day that we were able to remove total phosphorus. Otherwise, we have 0 total phosphorus removal. There was a little bit of dissolved phosphorus removal, 13%, 26%. So when we're looking at this data, we're wondering why we use iron hand sand, right? And the lab proved that iron hand sand is able to remove dissolved phosphorus pretty efficiently, but why we're not. So I'm just going to step back to that picture. So there could be potentially a couple things associated with this. So you see all the leaves that accumulate on top. We could experience some breakdown of the leaf that are actually releasing phosphorus back into the system. And the other thing is attaching the tray on the bottom. We're not just collecting water that went through the media and drains out. We might be collecting water that come from the site, the outside of the media. So like there's preferential flow path here. So it's really a mix of water of treated, untreated water, but it's still promising to see that E. coli was being removed from this. So our next one, it's the bench filter for the stormwater ponds, and this is the schematic with Minnesota filter and now with biochar. Let's see how that works. So we have a couple ponds that we selected. First one, this is right by the Champlain City Hall, and was this pond on the left side. There was the filter bench was printed. And here are some construction photos that you can see. We're laying down the media and the filter fabric, and this is, so I think this is when they lay down the biochar. So this pond is a sandwich, so it's iron hand sand, biochar, and iron hand sand. And there's a drain tile underneath. So this one was actually designed to be under the normal water level, so we can have the maximum amount of data available because waters keep flowing through. Although the standard design for Minnesota filter is asking, well, you're at the normal water level, you want it to be dry at some time, but we think it's not affecting as much because this is really, there's only like maybe 1 or 2 inches of water on top, and there's a lot of wind effect, so we're actually mixing in oxygen. It's not, it's inundated, but it's not anaerobic. So this is the after picture. It's kind of pretty, but it's even prettier when the plants come out. For Champlain, for this site, our total phosphorus removal, it looks pretty good until this year. There are a couple assumptions that we have for this year why this happens. We actually had a little bit design change and modification of the system, which I'll talk about in a bit. So for this year, we actually saw the pipe that floating up. First of all, because we're limited by the depth of how much material we can put down. So instead of using P-rocks, we use soft pipe. And it worked for last year until mid this year that the pipe floated up. So apparently there's not enough water going in, and there's too much air buildup in the pipe. So we're actually not doing any of the treatment. And then there was a lot of algae growth on the bench itself that could potentially contribute to the TP you see over there. Dissolved phosphorus is the same trend because the system targets to remove dissolved phosphorus. But E. coli still looks pretty good. So looking at E. coli from 2017 all the way to 2018, it's pretty much removing E. coli in every event that we sampled. And the removal efficiency is not on there. Anyways, so, and we did look at, so we were wondering, what's the cold weather effect on biochar? So we did look at the biochar in the office to see going through freezing and thawing cycles if it's going to break down, if it's going to affect the surface area of E. coli removal. But we actually did not see any of the breakdown. So the particle size did not change, and we preserved the surface area during the freezing and thawing cycles. And then the second location is at Crystal North Line Parks, and unfortunately, due to the difficulty of the supplier, we were going to do a replicate, but then it turned out to be a comparison. So this is iron hand sand only filter. And this is actually designed up to the standard. So this is right at the normal water level. 50% of the time this is inundated, there's water flowing through, and the other half is pretty dry. And then this is the construction picture of laying down the drain tiles underneath the steel soft pipe. As you can see, we have very limited depth to apply pea gravel. And that's iron hand sand on top. And this is a finished picture. Have this, that's funny, one is dry, one is inundated. And due to the width of it, we actually have 2 drain tiles underneath. So this is another nice picture. there's a lot of wildlife, so they're definitely contributing to the E. coli and phosphorus sources in this area. Here's the most original sampling technique that we used. First of all, we used a hand pump, trying to pump water out of that clean out, but it didn't work as well as we thought. So we actually did a system modification earlier last year to add a sampling port at the very end of the discharge pipe with the backflow preventer. So actually that works out pretty well. So for that, Crystal, for total phosphorus removal, it actually proves that the iron hand sand filter is efficient in removing total phosphorus versus dissolved phosphorus. So you can see that the percent of total phosphorus removal is actually less than the percent of dissolved phosphorus. So that system is targeting dissolved phosphorus match the lab results. And it also has that the E. coli removal is really not being removed. However, so if you remember that research Dr. Sanjay Mohanty did at the column study, that they're actually seeing 62% of E. coli removal from CN only, and in the field, it doesn't seem to be the case. It's not removing E. coli at all. And the third pond, this one is more a visual demonstration. So we kind of have all sorts of situations that happen during the field trials. So this one, again, due to the lack of material, we have half and half. So the lighter color half on the far side has biochar, no iron filings, so biochar with regular sand. And the half, the more reddish on this side, has iron hand sand only and no biochar. So we were going to try to let water flow through and compare it, but however, this is completely dry due to a potential leaky weir. And even after we completely sealed the weir off, it was still taking forever for this pond to fill up. So it's potentially oversized for the drainage area. So this is kind of a nice visual demonstration of what these two material looks like, and there is no data on this. And there's another picture. You can see that water level is actually lower than that filter. So to summarize these, we only have data from Chaplin and Crystal. So looking at E. coli, the one that Crystal, you see the 28% is on the days where E. coli is being removed. So we had like maybe 2 events where E. coli is actually lowered. Chaplin has 77%. And Crystal has 28. If that's the effect from the sand, then we're still seeing a little bit that proves that lab result could be valid. And then the total phosphorus removal, 39% at Chaplin, 54% at Crystal. It makes sense because with the same depth, Crystal actually have a higher percent of iron filings than Chaplin, because Chaplin has 30% of biochar. Dissolved phosphorus kind of a similar trend, and it's because we're targeting dissolved phosphorus, it makes sense it has higher percent reduction than total phosphorus. And to pull all the data together, so this is Chaplin, Crystal, both the stormwater pond with filter bench, New Hope, Robbinsdale, the 2 middle ones is the catch basin. The filter box, where is the filter box? I'm going to go back to that. So let's just look at that first. So Chaplin, the reduction, you can see that E. coli has the E. coli in Chaplin and Robbinsdale. So E. coli across this board, other than Crystal, is doing pretty well reduction by biochar. And then total phosphorus is fairly stable, other than Robbinsdale. And then the reason this filter box, which I'll show later, has the highest reduction of all is because we have the most controlled environment. So look at the filter box. The filter box located right at Weber Park, Minneapolis. That's the waterfall at Weber Park. So from a plan view, there's a little overlook platform next to the waterfall. So we divert water from the fall into a job box and then let water out back into the waterfall. And here's a schematic of what that jet box looks like. So in the box itself, we again have sandwiched iron hand sand, biochar, and sand, and the water comes in and goes out. Or it comes in from the top and just bursts across the surface, and then this one actually we had enough depth to use pea gravel. This is not sock pipe. So here are some field photos. So the one on the far end, that's just biochar, so there's another layer of iron sand that's supposed to go on. And that's kind of a finished look. The one on top is kind of a finished look after we installed the inflow pipe. So this perforated pipe where water gets dispersed to the surface. And here's a view on the other side where the pipe goes. So there's inflow, there's an overflow, so we don't flood the platform. There's an outflow going back into the waterfall. We had pretty good flow in 2017 and 2018 is kind of being, the flow's being low. And also we have an interpretive sign that explains how this filter works for public outreach and public education purposes. We also have a similar sign over at two of the ponds, right? Over at the Crystal Pond, the one at normal water level, and over at Olson Pond, the one that's below normal water level. And we received pretty good public feedback, so people actually stop by and read those. And when I was out sampling the site, I also have bikers coming by and asking what this is. But that was kind of creepy because you can't hear anything. The waterfall is really loud, and actually, I accidentally knocked somebody's head with a sampling rod. So, however, this system also had problems. The first year it ran pretty clean, but the second year we actually experienced a lot of surface clogging. You can see the black mucky material is coming out of all the ports and it's depositing on the surface, so no water is flowing through the media and coming out. So the reason we figured out why there was a lot of surface clogging is because there was a lot of TSS that is getting carried. We actually did measure TSS coming in and out, and we're able to remove 90% of the TSS. So they're all depositing on the filter media surface. So this is our first design of the inlet pipe. It's just simply an open pipe sitting on the ledge. And then there was a rock that is trying to block any leaves from going into the pipe, but it didn't work really well, so we had a lot of surface clogging. Then we installed an elbow that has a perforated pipe that is socked attached to it. So we try to filter as much TSS as possible before the water goes into the filter itself. And then we realized there's a lot of maintenance that needs to be done on that sock because that sock pipe gets clogged and still no water is going in. But after installing the sock, we have clean water flowing out of the inflow pipe, and then the system can work again. But it's the same as the filter bench that we have to break the surface bond a lot for water to move through the system. So here we have a little sampling port at the outlet pipe. You can see that's clean water coming out of that. So the filter, the utility box, looking at the results, it's pretty steady removal for total phosphorus. Again, this is the kind of a more standard design where we did not use a sock pipe for the outflow pipe, and we used P-rocks. And then this system compared to the other two is less affected by the different changes in the environment. And this is dissolved phosphorus. I wish I didn't have to show you that last one, but we don't really know why yet. This is the last sample that was taken in 2018, so at the start of 2019, we still have another flow season to sample, so hopefully we can explain why that dissolved phosphorus is coming out at the same concentration. But other than that last one, we have pretty steady removal of dissolved phosphorus as well. So looking at E. coli, so the kind of beyond E. coli concentration's been fairly low at the creek, but we do have some high flow events where E. coli is even exceeding the Q standard. So it's even higher than that where it stops, because it goes above that. But we were able to, for 100% of the event, we were able to reduce E. coli by well below the chronic standards at 94% average removal. So looking at the summary of all the removal efficiencies, the filter box was able to remove E. coli by 94%. Total phosphorus, so the scale is a little different and interesting because it didn't start at a 0%. So it started at 76, so they're actually really high. Total phosphorus by 83% and dissolved phosphorus by 87%. So if I go back and compare these systems, you can see the difference. Once you have a close to a lab setup, a very controlled environment, you actually more at a potential removal capacity. And the rest, it's still pretty promising to see that E. coli is being removed a lot, proving that biochar actually do work. But one of the things that we're interested in knowing is if there's going to be any, so is this just getting the E. coli attached to biochar itself? Does it grow any? Is E. coli being killed on the surface? Are we going to have any release? So that will be more of a 2019 sampling once we can see if there's any change in that dynamic. There's a lot of slides. I'm trying to go back here. I'm looking at those pretty graphs again, which is nice. So a couple of remaining questions that we still have. Can we characterize initial holding capacity or moving capacity of phosphorus from iron-enhanced sand? What happens to the water filter interface and does it affect the filter effectiveness? And what about the lifespan of this kind of systems? When do we need to replenish either iron-enhanced sand or biochar? And those will be interesting design questions to answer. And to answer, we don't have the answer for all of them yet, but here's the thing that we're doing for the first question, to looking at initial capacity, holding capacity of iron-enhanced sand to remove phosphorus. So from University of Minnesota, Dr. Beth Fisher, she helped us install some real-time sensors to measure DO, redox potential, water level, and conductivity. So there's like sensor buried underneath the filter media and sending back real-time data. However, we do not have that data yet, so it will be 2019 when Dr. Beth Fisher will help us with that. So here are some field. So they use this kit called Environmental DIY. They built their own kit. It's cheaper than most sensors, and it will send pretty good data back. So this is kind of the field picture of what the sensor kit looks like. And then what happens at water filter interface? I think I mentioned that we had the pipe flotation problem, and you can see that pretty well. The end of the pipe is floating up. So it's kind of funny that when that first happened, we thought, oh, we could just rebury the pipe. So we throw some ripraps over at the very end and rebury the pipe. I actually don't have a second picture, but a couple of weeks later, the middle part floated up, so it kind of looked like a broken elbow at some point. So then Ed and I went out. We raked a lot of, this is Ed at work, we raked a lot of algae from the filter surface. And then you can see the stock pipe have a lot of deposition on there. So Ed took his very handy, oops, I think I clicked twice. Very handy drill and drill into the pipe. We actually hear the release of air. So in addition to there's not enough water in the pipe to hold it down, we're actually having some microbial activity in the pipe itself that is releasing air. And then that's why the pipe floated up. It broke out of the media surface. There wasn't enough weight to hold it down. And then to answer the third question, can we estimate the average lifespan? I did take a look at, so this is based on iron-enhanced sand. We have no better way to look at biochar yet. what's the capacity of how much E. coli will be able to hold without release or losing capacity. But this is just for iron and sand. So we measured how much flow is coming out of the end of the pipe, and we estimated the depth of treatment per year, and looking at percent reduction. So we estimate that Chaplain Pond filter bench is actually roughly around the similar range of lifespan that Dr. Erickson does for his filters. It's around 9.6 years. And the filter box, because we have so little flow going through, and although with a really high removal rate, we estimate it to be 1,347 years before we need to replenish that material. So you can see that the treatment depth at Chaplain, the 9.6 years, is treating 1,008 meters per year, but the filter box is only doing 49 because there are time periods that we actually have no water going through. So in summary, that we know biochar works, but there's still a lot of questions that needs to be answered before this technology can be well applied, such as the actual mechanism of biochar removing E. coli. There are a couple theories or assumptions other than the physical absorption. Dr. Kurt Spolkas from the University of Minnesota actually mentioned to me that once you rub biochar on your fingertips, and you don't have to wash it, you can just rub it, and those dark spots are going to go away because the organic carbon particles are actually small enough to enter the cells. So there's a potential biochar could send carbon molecules into the cell of biochar or of E. coli and potentially kill it. So we don't know yet, but we haven't seen much of a release event in all of our field implementations. And then there's also other environmental changes that might impact the effectiveness of the filter, such as incoming water condition. Could be cold, could be warm. There's a high TSS level. Those can also affect the effectiveness of filters. And iron hand sand appears to have minimal effect in removing E. coli. Despite the lab test, there's a 62% removal. In the catch basin insert, we have stuff accumulating that could hinder the ability of phosphorus removal capacity, and the cold weather effect on biochar. So, after we will sample after the winter, but we might see some differences over the years. It worked for 2 years. We still don't know this year yet. So there are a couple of things that we learned from these field trials. I was going to put it all in caps because it's very important to not have soft pipes for this kind of filter system. It greatly hinders the ability for water to actually enter it. And you might cause flotation issues and frequent maintenance. We need to break the surface bond. In the spring, we need to remove any of the algae that's growing on top of the filter. So most likely weekly raking. Dr. Andy Erickson also mentioned that in his presentation as well, that weekly raking is probably necessary for these kind of filter benches. And for the pipes, initially we did not leave an air vent, and we kind of learned the lesson that instead of a capped clean out, it's probably the best to install some kind of rodent guard so the air can get released from the pipe itself to prevent flotation. And also filter pond and stream TSS. So filter pond, because the stormwater pond actually removes a lot of TSS, so we don't have as much of an issue than the stream. So the water coming off the stream that carries a lot of TSS that clogs the system. And also the reason that we had most of those issues, like the no stopped pipe and TSS, is that we were pretty limited. So we put the retrofit at existing stormwater ponds, but we were fairly limited to the sizing, the surface dimension, the depth of those filter benches. So instead of retrofitting old ponds, incorporating this technology with new stormwater pond construction would be actually better. And those conclude my presentation. Any questions? and amount of time.
What kind of impact does biochar have on the pH of water? Is it pretty significant?
We tested pH. It wasn't as significant as we thought for our filters. So I think in the lab it might be more significant because you have such a small inflow of water compared to the amount of biochar. But in those pond and stream systems, it actually neutralized it pretty well.
Okay. So that was part of the experiment too? You measured
Yeah, we
pH?
had some data points, but it wasn't enough to make a case.
Oh.
If you were to treat all the watershed, how many of these filter boxes would you need?
Sorry, what?
If you were to treat the whole watershed for bacteria, how many of these filter boxes would you need?
Filter boxes,
Yeah,
the catch basin?
Yeah,
or
catch
the-
basins.
Oh.
Several thousand.
As much as possible. It's going to be very difficult because it has such a limited capacity of treating it. So I think, what we recommend is the catch basin is not as efficient as modifying or incorporating into the new stormwater pond construction or even the stream diversion.
The reason we did the catch basin inserts and the utility box was it was just easy to deploy for us. Because we could get them in fast, because the utility box went in at Weber Falls where we have 12 feet of head to work with, which is really nice to have. And then the catch basin inserts we put out on Wenck Avenue in front of our emergency response office. And then the city of Robbinsdale's City Hall parking lot was the other site. So they're just easy to get to. I don't really know that they have a great application. I think if maybe there's a construction site or some site that has a high bacteria concentration or phosphorus discharge that they've got to deal with, yeah, probably. For our purposes, it was we could get in the field quickly and start getting some measurements.
Okay, thank you.
Biochar is also being considered for use in bioretention systems. Do you have any thoughts about how it might perform in those systems? Would it behave differently, or any suggestions for?
We don't have any application in the bioretention systems, but I think biochar, people implement biochar in those floating wetlands, trying to remove, those Brotex material and incorporate biochar in there and trying to remove phosphorus. I think, actually resin time is probably playing a more important role in any of the systems for biochar to remove. But what kind of bioretention system you're mentioning? What type of nutrient are you targeting?
Be phosphorus primarily.
So my master's thesis that I did test the ability of biochar in removing phosphorus and nitrogen. It was removing about 30% of the phosphorus. So it has capacity, but then we weren't sure how it's removing. If there's hot spots in the system that is depositing phosphorus, or if there's going to be future release. So so based on the research data that I've seen, I wouldn't recommend that's a very efficient way in removing phosphorus, because the thing with nutrient removal, if it's biological, biochar actually have a really long start time compared to wood chips. So it's a form of carbon that is harder to break down for microbes. So unless you have a kickstart mechanism like liquid carbon, it takes super long for it to stabilize over time, and it just wasn't a very efficient way of removing it.
Do you know how your results would compare to other applications of iron sand filters that have been tried elsewhere? Have you come up with comparable results, do you think, with some of those studies, or do you know?
I don't think we've compared them. We do have comparable problems. I've been to Andy Erickson's presentation, and I think the treatment depth is fairly comparable, and the fact that the surface bond that needs to be raked is fairly comparable. But based on the literature value, I think our efficiency of removing total phosphorus is comparable. to those values, but I think it's a good idea to take a look at others, like field trials to see if ours is comparable as well.
So maybe I missed it, but what is the mechanism that is making biochar effective in removing E. coli?
So, it's probably too far, I'm not gonna go back. So I do have a slide that showed that biochar gets, the E. coli gets attached to biochar particles. So it's, one of the assumptions is more of a physical way of removing by absorption.
So what I think the comparable analog is the water treatment filter I have in my refrigerator. That's activated carbon. Biochar is a poor version of activated carbon because you get it by the ton or the cubic yard. So that strips really all organics out of for my water treatment. So I think it's doing a comparable thing here, that it's not just targeting E. coli, it's taking most organics out as it flows by.
Okay, thank you.
And so also another thing we're looking at is, from a design purpose on my side, how do I size this? And our purpose is, well, we put in as much as we thought we could, and biochar is cheap, so let's put it in as much without having to become buoyant. Well, that's not much of a design parameter. So on my water treatment side, Home Depot recommends changing them, or GE, the filter manufacturer, recommends changing them every 6 months. So my wife really wanted me to do that, and I thought, I don't want to throw money away like this. It's just my wife and myself at home now. It's not our kids. So really, what is the flow-through pattern for these water treatment filters? So I called GE up, and they gave me how many liters it actually flows through. So my wife and I go through, I figured about we should change it every 2 years. So I think if there's some analog, and maybe I can go to GE, who manufactures these for activated carbon, and get some sense of how much water you can actually flow through with the amount of contaminants in it to see what's the likelihood that you're going to get some breakthrough at some point.
Thank you.
As you can tell, it's pretty infant where we're at. This is like garage store or garage just stuff to work on.
Well, we don't have any more questions. Hey, thanks for coming over and telling us about your project.